So we have reached up to the resonance theory. Up till now we have discussed rule number 1. That is, the structure must be differentiate, or there must be change in the only arrangement of electrons. Rest of the structure or the nucleus will be same, or there will not be any change. Rule number 2, every contributing structure will give the hybrid structure, or the energy content of the hybrid structure must be same. Rule number 3, resonance hybrid structure will be most stable structure amongst the remaining number of structures. So this we have covered up till now. Now next, there are compounds which are not from the family of benzene ring, which are not aromatic at all, but then also they are going to give the resonance. So there can be a resonance only between the structures that contain same number of odd electrons. This is the case, or this condition is only applicable to the non-benzenoid compounds or aliphatic compounds. In that case, they should concern about the restriction only in dealing with the diradicals. Though all these compounds which are aliphatic in nature, they must contain a presence of odd electron, and those are all diradicals. So these molecules that contain 2 unpaired electrons, these cannot be resonance. There will not be a resonance. See, the 2 unpaired electron means those are all even number. But the aliphatic compounds which are having odd number of electrons will give the resonance. Now, these are the 2 resonating structures of benzene given by Kekulé. The Kekulé structure 1 and 2 now immediately recognize that meet the conditions for a resonance, that is structure that differ only in the arrangement of electron. See, so these 2 structures are same, only there is arrangement of number of double bond, or the arrangement of double bond will be shifted from one carbon to the another. So these 2 structures are resonating structures of each other. Benzene is hybrid of 1 and 2, since 1 and 2 are exactly equivalent. See, these are 2 resonating structures, they must be equivalent. There will be only change in the position of electron. Rest of the atomic nuclei or rest of the structure is same. There will not be any instability in the structure, and the hybrid structure will have most contributing structure. So the benzene is hybrid of structure 1 and 2, since 1 and 2 are exactly equivalent and hence of exactly same stability. They make both these structures, structure 1 and 2 will make equal contribution to the structure of hybrid, and also 1 and 2 are exactly equivalent. Stabilization due to resonance should be large. Now we are interested in the discussing of orbital picture of benzene. We know all about orbital theory. What is the meaning of the word orbital? Which are the orbitals? 1s, 2s. These are the orbitals of carbon atom. So carbon atom is orbitalized into 1s2, or if we write the orbital structure of carbon atom, or electronic configuration of carbon atom is 1s2, 2s2 and 2p2. So how the benzene molecule will be represented in the orbital theory? So more detailed picture of benzene molecule is obtained from a consideration of the bond orbital in this molecule. Since each carbon atom is bonded to 3 other atoms. See, if I am going to discuss or consider about this carbon atom is bonded to this carbon atom and 1 hydrogen atom. So each carbon atom in the benzene ring is bonded to 3 other atoms. So it uses generally which type of hybridization? sp2 hybridization, as in the case of ethylene. Ethylene, CH2, CH2. So in the case of ethylene also, carbon is bonded to one carbon atom and two hydrogen atoms. That means three other atoms. In the case of benzene also, every carbon atom, see, every carbon atom is attached to two carbon atoms and one hydrogen atom. So the geometry is same. Each carbon atom is bonded to two other atoms. So these lie in the same plane. This arrangement will be lying in the same plane, that of the carbon nucleus, and are directed towards the corners of equatorial angle, equatorial triangle. So the band angle in between these all carbon atoms is 120 degrees. If we arrange all six carbons and six hydrogen atoms of the benzene to permit maximum overlap of these orbitals, we obtain the structure which is shown in the figure. So this is a planar structure of benzene in which carbon atom is bonded to two carbon atom and one hydrogen atom. So the bond angle in between all these carbon atom is C. The bond angle in between all carbon atom is 120 degree centigrade, because there is formation of an equatorial triangle. So we are going to obtain the structure which is there in the figure. So first structure will represent only a sigma bonds. So these are all about sigma bond. There are two types of bond, sigma bond and pi bonds. So the bond which is shown in this planar structure is sigma bond, and this aromatic or arrow diagrammatic representation is of related to pi bond. We will go in detail about this. Benzene is a flat molecule. See, here we have drawn the structure of benzene. It is a flat molecule with every carbon and every hydrogen atom lying in the same plane. See here, all the carbon atom and all the hydrogen atoms are lie on the same plane. So we can represent the structure of benzene in a single plane of paper. It is very symmetrical molecule. If we can divide the structure of benzene in any manner, so it is very symmetrical molecule with each carbon atom lying at an angle of regular hexagon. Every bond angle is of 120 degree. Each bond orbital is cylindrically symmetrical about the line joining the atomic nuclei, and hence, as before, these bonds are designated as a bond. Again, we will go in depth into the atomic orbital structure of benzene. The concept of hybridization of atomic orbital theory of resonance developed by Linus Pauling in 1930 provided the first adequate description of benzene molecule, as it is bonded to the central carbon atom is bonded to two carbon atom, and a carbon atom is bonded to in the case of ethylene, a carbon atom is bonded to one carbon atom and one hydrogen atom. So the bond angle in both the cases 120 degrees centigrade. For this type of bonding, carbon uses sp2 hybrid orbitals. For this type of bonding, carbon uses sp2 hybrid orbital. Each carbon forms a sigma bond to form adjacent carbon by the overlap of type of hybridization is sp2 hybrid orbitals, and one sigma bond, that sigma bond is formed between the sp2 orbital of carbon atom and one s orbital of hydrogen atom. So all the carbon and atom bonds in the benzene are of same length. See, all the carbon atoms in the benzene ring, the length is same. It is generally 1.39 and strong. A value almost middle way or midway between the value or bond length in sp3 hybridized carbon, it is 1.53, and that of double bond between the sp2 hybridized carbon is 1.33. So this is basically an average of these two values, that is 1.54 and 1.39. Benzene is going to obtain a generally midway value. It is 1.39 and strong. So this is a planar representation of benzene molecule with the help of sigma bonds. What about pi bonds? So this will be the representation of benzene molecule when we are representing their pi bonds. Each carbon also has single unhybridized 2p orbital. What is the electronic configuration of carbon? 1s2, 2s2, 2p2. So those two electrons are arranged in 2px1 and 2py1 orbital. So those two electrons are unpaired. So each carbon atom has single unhybridized 2p orbitals that containing 1 electron each. These 6 2p orbitals lie, all these the p orbitals are represented in this dumbbell shaped manner. So all these unshared p orbital electrons are lying perpendicular to the plane of the ring and overlap to form a continuous pi cloud. So there is an interaction or there is attraction between this electron, this pi electron and this pi electron of this carbon atom. There is interaction between all these pink colored pi orbital electrons and they are going to form a cloud, attraction cloud encompassing all 6 carbons. The electron density of pi system of benzene ring we're going to show a one tallness or donut shaped region. So all these pink colored p orbital electrons will overlap in between itself and they are going to form a donut shaped region above the plane of the ring and below the plane of the ring. So they are going to show the two donut shaped regions. One will be above the plane of the ring and one will be below the plane of the ring. Orbital overlap model of bonding in benzene. So what is the diagrammatic representation is? First, a carbon hydrogen framework, the six 2p orbital each with 1 electron are shown uncombined. And second diagram is donut shape region which will be formed above the plane of the ring and below the plane of the ring. As we see that the chemical properties of benzene are just what we expect from the structure. Despite delocalization, the pi electrons nevertheless more loosely held than sigma electrons. So those are all pi electrons which are there in the p orbital of carbon atom. All carbon atoms are generally loosely held than that of sigma electrons. The pi electron thus particularly available to a reagent that is clean electrons. A typical reaction of the benzene ring are those in which it serves as a source of electron for the electronic or for the electrophilic reagent. Because of the resonance stabilization of the benzene ring, these reactions lead to the because of all these reasons, benzene will not allow easier entry of any compound in the ring. So they are generally going for which type of reaction? Substitution reaction, in which the aromatic character of benzene ring is preserved. So this is all about resonance which is given by the benzene ring. What are the reasons behind those benzene ring? What is the orbital picture of benzene ring? This we have seen. Now we are moving towards the one of the basic property of benzene ring is aromaticity of benzene ring. Now what is the meaning of the word? Why benzene is aromatic in nature? This we are going to study. So we know up till now we have defined all the aromatic compounds are those compounds which will resemble, which will appear like the structure of benzene. But just with the property of benzene but by looking similar, by resembling the structure of benzene, those all structures or those all structure which will resemble the structure of benzene, whether they are all aromatic, yes or no, we don't know. So beside the compound that contain a benzene ring, There are many other substances. They will not look like a benzene also, but they are aromatic. Yes, some of these superficially bear little resemblance to the benzene. So what are the criteria behind aromaticity? Aromatic compounds are cyclic, generally containing 5 or 6 or 7-membered ring, and when examined by the physical methods. So first property is they must possess cyclic, or they must be cyclic in nature. They are all have either 5, 6 or 7-membered ring. They are all found to have flat molecules, and their protons will show a single shift in the NMR spectra. From a theoretical point of view, aromatic compound must have a molecule that contain cyclic cloud of delocalized pi electron. Just we have seen the cyclic cloud of pi electron which is there in the benzene. This is the cyclic cloud of pi electron which is represented in this diagram related to benzene. So second criteria for aromaticity, they must have cyclic cloud of delocalized pi electron which is above and below the plane of the molecule as like that of benzene. Furthermore, the pi cloud must contain 4n plus 2 pi electron. This is very important one, and this is the theory of aromaticity, and this rule is given by one of the scientists, that is Huckel. That is to say, for the particular degree of stability that characterizes an aromatic property, delocalization alone is not enough. So if any compound is must be aromatic, so there will not be any single property that there must be a presence of delocalization of pi cloud. This is not only a sufficient property that compound is aromatic. There are another rules for that, and those rules are represented by Huckel. That is, delocalization cloud is not enough for that compound to show the aromaticity. There are rules. There must be a second rule. A second rule is there must be a particular number of pi electrons. What are those particular number of pi electrons? There may be 2, 6, 10. Likewise, not all even number. So there is criteria for the compounds. Those are all have 2, 4, 6 number of pi electrons. This requirement called as 4n plus 2 rule. So presence of delocalization cloud is not only enough to show aromaticity. There must be a presence of particular number of pi electron. This is the second property, and this property is known as 4n plus 2 rule or Huckel rule. As this rule is given by the Huckel, that rule is known as Huckel rule, and it is based on the quantum mechanics, shape of the atoms and all, and has to do with the feeling of various orbitals that make up the pi cloud. The Huckel rule is strongly supported by all these facts. So there are examples of some of the compounds which are aromatic and which are not under the category of aromatics. Let us take some of the examples. Some of the evidence is supporting the Huckel rule. Benzene has 6 pi electrons. So 1 pi electron belongs to, or 1 pi bond with respect to 2 electrons every time. So benzene have 3 number of double bonds. That means he is going to possess how many pi electrons? 3 multiplied by 2, 6 electrons, and the aromatic 16. 6 is of course a Huckel number. What are the Huckel numbers? 2, 16, 14, 18, 22, 26. These are all Huckel numbers. So 6 is the, of course, a Huckel number corresponding to n is equal to 1. Besides, benzene and its relatives, naphthalene, 2 number of benzene rings, conjugated. Anthracene, 3 number of benzene ring conjugated. Phenanthrene, 4 number of benzene rings conjugated. All are under the category of aromaticity. Now we shall encounter a number of heterocyclic compounds that are clearly aromatic. These aromatic heterocycles we shall see are just the one that can provide an aromatic sextate, or as further examples considering the 6 compound for each of which just contributing structure. So there are some of the examples given here with respect to the aromaticity. In the first one, the structure of cyclopentadienyl cation. Why cation? Because one of the electron from this carbon atom is withdrawn. So this carbon atom is going to possess an positive charge. One of the pi electron is removed. So he is going to have the positive charge. So number of pi electron in this case is 2 pi bonds means number of pi electrons 4 pi electron. 2 multiplied by 2, 4 pi electron. In this case, it is an cyclopentadienyl radical. So in this case, it is an radical. That means all the 2 electrons removed. So, okay, radical means one of the electron is here and one electron is removed. Here in this case, all 2 pi electrons are removed from this carbon atom. That's why he is going to possess a positive charge. In this case, one electron is removed and one electron is retained by that molecule. It is understood. So, the number of pi electron in this case is 5. Here, see, all the 2 electrons are there. That is cyclopentadienyl anion. All the 2 electrons are removed. Cyclopentadienyl cation. One electron is removed and one electron is retained in the structure. So it is cyclopentadienyl radical. Now out of these 3, while we are comparing these 3 structures, our Huckel number is given by this structure. Which structure? The cyclopentadienyl anion, as he is going to give 6 number of pi electron, so that the structure is aromatic in nature. See, up till now we have seen criteria for aromaticity. First one, the structure must be cyclic. Second one, the structure must be planar. Third one, there must be delocalization cloud of electron, and very important and final condition is they must have beer for n plus 2 number. Now what are these Huckel numbers or for n plus 2 numbers? 2, 16, 14, 18, 22, 26, 30, 34. So these are all Huckel number. So there must be a Huckel number. See, all the criteria are satisfied by this structure. So this structure is aromatic in nature. Now we will proceed for the next example. Now next example is cyclopentatrienyl cation. Now in this case, we have known that fourth condition, the structure must have either 5th member ring, 6th member ring or 7th member ring. Now in this case, ring is 7 member, but the name of the compound is cyclopentatrienyl cation. That means from this carbon atom, all or 2 pi electrons are withdrawn. That's why this carbon atom is going to possess a positive charge. Then also this carbon atom or this compound is aromatic because the remaining 6 pi electrons, these are inside the ring, will obey the rule of Huckel. That is 6 number of pi electron. That's why this compound is aromatic in nature. Now rest of the properties or rest of the condition is already preferred by this compound. It is cyclic in nature. It is planar in nature. There is a delocalization of cloud of pi electron. And very important property and last property is 4n plus 2 rule, which is also obeyed by this compound. That's why this compound is aromatic in nature. Now next, cyclopentatriene radical. That means one electron is removed and one electron is retained on this carbon atom. Now this structure is going to possess 7 number of pi electrons, which is not under the category of Huckel rule or 4n plus 2 rule. Now remaining properties are satisfied by this structure, planar, cyclic in nature, but he is not going to obey the last rule, that is Huckel rule. So the structure is non-aromatic. Now next structure, cyclopentatriene anion. Here there is presence of 8 number of pi electrons. All the p orbital electrons from this carbon atom are retained. It is there. Then also the compound is non-aromatic because they are not going to possess number of electrons which will obey the Huckel number. So out of this all 6 number of compounds, only 2 compounds are aromatic, that is cyclopentatriene and cycloheptatriene cation, because only these 2 compounds will obey all the rules of aromaticity. Now, how we can determine the aromaticity of the compound? Many other types of molecules beside benzene and the derivatives, they are aromatic in character. That is, they contain high degree of unsaturation. It failed to undergo characteristic alkane addition and oxidation reduction reaction. But a principle underlying the aromatic character will be given by a clever physicist, Huckel, who had solved the problem of determination of aromaticity in the compound. Now, these rules we have already discussed. Just we review it again. First rule, they have 1 2p orbital on each of its atom. The structure must be planar or nearly planar so that there is continuous overlap of p orbitals. And third and very important rule, they must possess presence of Huckel number pi electron 2, 4, 16, 2, 16, 14, 18, 22, likewise, and so forth, number of pi electrons in the cyclic arrangement. This third rule is known as 4n plus 2 rule or Huckel rule, because the aromatic number of pi electrons can be determined when n is substituted by any of the integer, that is 0. Benzene meet all the criteria, that is it's cyclic in nature, planar in nature, 2p orbital cloud, and it has 6 number of pi electrons. That's why it is aromatic in nature. Now we are discussing again next examples, that are pyridine and pyrimidine. We will determine whether these compounds are aromatic or not. So pyridine and pyrimidine are heterocyclic analogs of benzene. As the name of the topic itself suggests us that benzene and its derivatives. So these are 2 compounds are the derivatives of benzene. In pyridine, 1 CH group of benzene is replaced by nitrogen atom, and in case of pyrimidine, 2 CH groups are replaced by nitrogen atom. Now first we will discuss about pyridine. Each molecule meets the Huckel criteria for aromaticity. Each is cyclic and planar, that is pyridine is cyclic and planar, has 1 2p orbital on each atom of the ring and has 6 number of pi electrons. See, inside the ring there is resemblance to the benzene ring. So they are all having 6 number of pi electrons. In pyridine, nitrogen is sp2 hybridized and its unshared pair of electron occupies an sp2. So this pyridine is sp2 hybridized, or the nitrogen atom in the pyridine is sp2 hybridized, and its unshared pair of electron occupies an sp2 orbital, which is perpendicular to the remaining p orbitals of the ring. In pyrimidine, neither unshared pair of electron of the nitrogen is a part of pi system. So the electrons which are there on the nitrogen atom will not be the part of this cyclic cloud of pi system. So this orbital is perpendicular to the remaining p orbital, and those electrons of the nitrogen atom will not be the part of aromatic system. That's why pyridine is aromatic in nature. Now, determine whether a lone pair of electron is a part of the system or if it is not a part of the pi system. First, we will determine whether the atom containing lone pair of electrons is a part of the double bond. If it is a part of the double bond, it is not possible for the lone pair to be part of aromatic pi system. If we discuss this is a part of the double bond, that time the compound will not obey the Huckel rule. That time the number of pi electrons in the system will exceed to 8 number. These are 6 numbers and plus 2, which is given by the nitrogen atom. So this will exceed the number of pi electrons. So the compound will fall under the category of non-aromaticity. But this is not the case with this pyrene molecule. Inside pi cloud, on the electrons which are inside the ring, these are sufficient to give the aromaticity to the compound. That's why pyridine is